Okay, hello. So this is the second part. Where I will talk about RTOS, fully designed by from the scratch. So its name is littleOS. You will see this also as an app for a bare metal project. So here you will see we compiled this littleOS and I just copied that littleOS. Then after that by same method I will just load the binary, not demo.bin. I will load littleOS.bin. Before that, if I show the ls, so here is littleOS.bin. Then I will load this littleOS. Okay, and then just go command. Okay, go on that address. So our littleOS is booted. Uh, so what happens? Okay, after booting, it will say that the binary of littleOS take BSS section for 538 KB. Okay, fine. The dot data section. Uh, if you know the if you have some experience with the debugging or actually how the binary file look, compiled binary file, you will have an idea. So the in dot text actually there are instructions, binary instructions. So the start address of dot text is on the address this because we loaded our binary on this, and the size is 44 KB. Okay, it's all okay. Just some RAM's monitoring. Okay, RAM monitoring. And then what happened? While booting, you will see the in square bracket. I copied this from how Linux kernel boots. Okay, because they write things in a square bracket. Okay, so while booting, it initializing scheduler, then a task registry. So there are 32 threads right now. Each thread have 16 KB of stack size. You will see that if you go to include and not shared logs, my bad, multitasking, no, common macros, yeah. So in common macros, actually, we define macros like hashtag define in each header file. Okay, but I keep this common macro file. Just I don't know why I like the centralization here. Uh, so the multitasking macros. Okay, so the thread stack size is 60 into k. This is 2 to the power 10, so 16 kb, and the max threads are 32. So 32 kb, 32 threads, you can use maximum 32 threads, and this is RR time quantum. For round robin, the time quantum is 20 milliseconds. Okay, you can change it from here and then compile and then load. Okay, so it took around 593 KB only. Okay, so actually you can go to set max threads up to 1000, 2000 also. But then my scheduler is very simple when I will show. So it will be better to keep this 32 number as a small as possible, the max thread number, because then our scheduler will be more responsive. Okay, so what CLI thread? Okay, so there is one thread which is continuously running and which is accepting your manual inputs. Okay, the backspace, when you enter, then it will print. When you hit enter button, it will see what you entered, and according to it will start a thread or make some work. Okay, if you enter only a question mark or help, if you type this help, then CLI thread is printing the help for you, like how normally all anywhere you will see this kind of help command. So what commands are available? One is kill, a very important command, because you want to kill some thread, you will give the thread ID, or you want to just kill all the threads. Okay, then a clear command. I love this command because it clears the terminal. Then the one is to reboot, restart, or reset. It will hardware reboot. Okay, then one is shutdown. It actually is not shutting down. I don't know, I have to just work on this, why I'm not able to shut down this NXP board. Okay, so next is share. To change the scheduling, there are three options. One is RR round robin, PRI priority scheduling, EDF for earliest deadline first. Okay, another is date time. It will actually show you what is date and time right now. So if you enter the command only, then it will show the help, like how to use this. If you then you will see here, okay, date time show, it print the current time. Fine. So date time show, it will print current time. It is saying uh, right now its time is 0 hours 4 minutes 37 seconds and the date is this. Obviously this is not correct, but actually we will correct this after some time. Okay, so then what? So now the dynamic task. What are these dynamic tasks? Actually, if you want to add some task to this little OS, okay, then you go to this tasks directory. Okay, then create a .c file only. Okay, like echo.c. Then there should be one first comment called task name and whatever you want to give this name. Okay, so the task name is debug echo, and what it does, it just take a argument, okay, which command line passes to it, and then just prints it. Okay, so now if you just write this task as .c and then compile, there is one Python file, the build task.py. It will actually grab all the .c files and then create a thread for them and assign this .main function to that thread to execute. Okay, and you will use this echo as a command line to invoke this thread. Okay, in LED or in ESP, you will use this ESP as a command line to invoke this thread. Like if I type this ESP, you will see ESP thread is printing something. Okay, it is actually printing the uses or help for ESP. Okay, if I print the echo, it is just printing echo thread because echo's work is to just echo something. Like if I type this, echo thread is printing this. Okay, okay, so the addition of the task to this little OS is very easy. Just to create a file, give it a name, and the main thread should have name like this echo should match to this echo.c's echo and underscore thread. Okay, that's it. Then you can do whatever you want. And one more thing, there is a, if I see, there is a another command called rest test statistics. Statistics is a very helpful command, or you will say a very helpful thread. There is a code for statistics.c also. Okay, so if you enter the statistics, it will say that statistics show, or you want to send your statistics to some target IP or untarget port or remote IP remote port. If I enter the statistic show, so sorry, so those are all statistics. The uptime is 30 minutes. The algorithm is round robin. Okay, and the current algorithm, and these are threads. So there are only 12 threads active, or you will say 12 threads created in the littleOS right now. Maximum size is 32, but currently only 12 threads. And you will see the states for each thread. If you remember the states like ready state, new state, terminated state, block state, so all those states are implemented. So for that you will see the code in source and the multitasking.c. Okay, you will see the how we are maintaining the states. Like if you create a thread, then it will assign the thread's current state as a state new state. Okay, like that only. So the three threads are ready. While I was printing this, of course the statistics thread was in running state because it is the printing the actual data. Okay, and all are new. The echo thread is terminated because we used that echo thread. Okay, it took TAT turnaround time in millisecond. It took 21 millisecond to print those. So one thread is CLI, which is ready state. It is continuously listening to our manual input. Okay. One is ESP Wi-Fi listener. I use the ESP Wi-Fi module to actually communicate via Wi-Fi also. And one is RTC daemon. It is actually updating current time. Okay, like after 1 second, it will update time by 1 second, like that only. Not synchronization for now, but I will synchronize this. Uh, then LED control, task new. I will show the print task. Okay, the one is print X, one is print O. Uh, to run print X, this is the command. To run print O, this is the command. Okay, so if I run this print 100x, it will print 100 times X, and it will print X, then 50 millisecond delay, print X 50 ms delay, and that all. If I print X, okay, if I just copy this, if I print O and then print X, okay, like that, so you will see both threads are printed. So the concurrency is very well maintained. And I entered the print X after, so the work of print X done after. Okay, now if you see the statistics, then you will see the X state is terminated obviously, and it took 6,000 seconds. O print O's state is terminated, it took 6,000 seconds. One little just thing, if you see this name, actually this name is taken by like I told you, right? So you have to write this first command comment. Okay, so from this the Python script take the name of the thread and set that name to that thread. Okay, so now I said like if we see the code for print X or print O, both are exactly same, just printing X and printing O. Okay, so it is just printing O, they sleep for 50 milliseconds and for 100 times, right? So it should take 5000 millisecond time, but no, actually what happened, when his 50 milliseconds are done, but the another thread was captured the CPU, so it had to wait until his choice came to it. Okay, so for actually a better time precision, if you see the a print 100a, it is just atomic print. What it will does, it will first stop the scheduling, it will print 100 times and then it will start the scheduling. Okay, and the command to run that is a print 100a. So I will run a print 100a. So you will see now I can't write on the terminal also. Now those three characters are printed here. Okay, actually if I run this all and then I hit enter, and if I show that what is statistics, so the exact 5000 millisecond for this atomic print is. Why? Because there is no scheduling. It's exact. So you can actually stop the scheduling in between threads. Okay, great. Then what will be the next thing? When there are multiple threads, the main problem is of race condition, right? So there, to test the race condition, actually I will show the code. There is a, where is that race test? Yes, race test.c. So here we are making four threads. Okay, two threads like race slave 1, slave 2, slave 3, slave 4, four threads. Okay, the two threads will work on func increase, and the two threads will work on func increase with mutex. Okay, so what are those? The one function is just increment a shared counter by this value, and func increase with mutex. What it will do, it will first lock a mutex, then only increment and then unlock the mutex. All other code is exactly same. Okay, so we are just running the thread 1 and 2, and then we are printing the what actually we get the value of shared counter, what is the loss, and the same for thread 3 and 4. Okay, so if I run this res test, okay, you will see that expected was this number, right? But we got outcome as this and loss is this. This is when by two threads without using a mutex. Okay, and this outcome is exact when by two threads with mutex. So actually, why this happens? That will be easy. It easy to understand. Uh, that happened actually due to race condition. So for this mutex, actually, if you see in shared locks.c, this is a function where we use this function of GCC that actually in backend use LDXR and STSR loop, which is like atomic operations. You can say that atomic operations. Okay. Uh, so the mutex is covered, and now what things are implemented? Now the flagship, I think now the only flagship thing is remaining, which is ESP thing, Wi-Fi thing. Okay. Before that, LED and sonar. Actually, sonar LED. If you see LED, you can on and off. Actually, there is no camera, so I cannot show how LED is turning on or off. You can see LED on green, then it will turn on green LED. It will blue, then it will turn on blue LED, and that. So there is one thread. Okay, it's okay. Now ESP thread. This is a very interesting thing. Okay, why? ESP, by using this ESP Wi-Fi model, we can actually communicate with Wi-Fi. Okay, so if I see what is ESP status, so here operating mode is one. Okay, and it's if connected to router, no. If in station mode, if one that means station mode. You can see the documentation for ESP or AT commands on internet also. So actually, if I want to put this ESP in ST mode, there are two modes: ST mode, AP mode. In AP mode, it will act as access point mode. So it or ESP will act as a router. Other devices will connect to this ESP. Okay, so like if I set the ESP AP mode, okay, then you will say that access point littleOS is now broadcasting. If I go to Wi-Fi, it will search. Okay, this is my router actually in my room. Okay, you will see this littleOS. Okay, so this is actually ESP. Our ESP Wi-Fi model is acting like a router, but I want to connect to my router. Okay, so for that ESP STA mode as a station mode, it will act like our mobile phone's Wi-Fi mode. And if you see STA mode requires SSID name and SSID password. I will connect to Sri Tenda. Obviously, I will change the password. So mode Sri underscore Tenda. Okay, the password is okay. That's it. Now, okay, it is now connecting. It will take 1-2 seconds or maximum 20 seconds, I think. Or it should be connected. Sri Tenda. Okay, and all is correct. Okay, it failed. I don't know why it happens. ASPRANE. I will try one more time. The name is correct. I think this time it should be connected. Okay, it's not connecting. What I will do, I will just reset my board. Okay, and then again that fat load command. I will just do that in a second. For that, I will copy it from above. Fat load. Okay, fat load and then go on 0x8 1 2 3 1 2 3 4. Okay, now if I run ESP and ESP STA mode, station mode, and I will connect to Sri Tenda. The password, now it should be connected right now. Okay, If it won't connect, then there is some Wi-Fi issues to my router also. Oh, the password is wrong. My bad, my bad. PIRNE, my bad. The Wi-Fi is connected. My bad. I was entering the wrong password. So now ESP is connected. If you see now ESP status, you will see the what IP address and MAC address it have. Okay. So what ESP can does? If we run a Python web app, okay, which is running on some remote server. Okay, let's think about this. We can actually send the statistics to this web app using the statistics command. Statistics send to. Okay, so statistics send to. Now what is IP address of that remote server, which is 192.168.0.100, and the port number is not 500. Actually on 500 it is serving a web app, but on port 5555 it is actually communicating with, or it is actually listening, so that is someone sending data to him or not. So send to this. So TCP data sent successfully. You will see the dashboard or the all thread states here. Okay. And if I open the ESP TCP server, okay, a TCP server is running and listening. So I will do like this. Okay, it will be okay. And if I run, suppose echo hello, so it got ESP is saying it got some exec echo hello from a remote server, and echo thread actually ran and it printed hello. So like that, if I enter help, it will just print the help. So we are giving remote commands. Okay, I can LED on green. Okay, then the green LED on the board is now currently on. I cannot show, sorry for that. LED off green. Okay, so also you will see here the states. Okay, so ESP Wi-Fi listener is continuously listening, so that is anyone giving any data to me or not. Okay, if you see now here, if I run this print x, okay, print x, for that first if I run one command, okay, which is a static from anywhere, suppose I run from this statistics send to command. Okay, statistics sent to this. And one more thing, my bad, just one more thing I want to show, that the syntax, you can use dashes for silent mode. You don't want to print anything from that thread, dash and, so that how many times you want to run that. Like if I run echo hi and with dash and 10, so it will, that thread will be started for 10 times. Okay, uh, if I say for 5 times, and then dash PR for period, and period of 1000 millisecond, so that each 1 second it will run this thread. Okay, so what I will do, if I send that statistics, you see this uptime. Okay, I send this one time, the uptime is updated, all things are updated, but I want that it should send continuously. So I will say the number of times -1 for infinity, and period is 1 second, and dash is for silent. I don't want to see these messages, okay, on the terminal. If I enter, okay, okay, all things are done, you will see this uptime is continuously running now. Okay, because each second our ESP or our NXP is sending data through ESP to the Python. Okay, and we are looking at this. Okay, now if you see what is state of print x, which is new state. Okay, now I will run this print 100x, okay, you will see the state is ready, okay, or blocked, or ready or blocked. It can be anything. Why ready and blocked? So for that, if you see, this is very interesting actually, this is very interesting topic. If you see the thread states, so one thread is ready, then a scheduler, if scheduler chooses threads from a ready state, okay, if thread is running, then it is in run state, okay. If its time quantum is ended or scheduler chooses another thread, then the thread which is currently running, it will go to ready state, okay. But what happen if thread is calling a delay for 50 millisecond, okay, it is not good idea to give a CPU to that thread for 50 millisecond where it is doing nothing. So actually what thread will do, it will go to a block state, okay, because it is waiting, and it will preempt the, or it will leave the CPU, so that the next time scheduler will put another thread which is in ready state to that. So sometime you saw the print x is in block state, sometime you saw print x is in ready state, okay. uh, so this is all what is happening. And the now the last thing is date time actually. What I told that if I enter date time show, this date time is very incorrect, right? Now date time have one more command. If I run date time, one more command which is date time sync or date time set. We can manually set the date time, but it's not that much that interesting. So I will date time sync uh, the your date time server IP. Like you know, this time is actually synced with actual servers, okay, who provides the current time of India. So sync server IP is 192.168.0.100 and port is 5555. The same server which is running the Python app, which is looking for is any TCP data is coming to that. Same server will provide date time sync to us. So if I run this, awaiting callback, yes, hardware clock updated successfully. If I run date time show, you will see current time is 15:53:34. This is 3:53 p.m. and the current date is 21/4/26, which is 21 April. So all this actually what is happening, and here the Python server is running. There is command nc, okay, nc listen on port 5555. What happens actually if I run this the date time sync on this port, this IP, so our NXP will send TCP data through the ESP to actually what I run date time sync, say, okay. uh, oh wait, actually what happened, so that statistics thread is continuously running. So if I listen on port 55, after 1 second, it will automatically see the status, because that stat what this is actually what statistics send to thread is sending data. So this is sending the status, the current algorithm, each tasks, the status, what is turnaround time, all things, the ESP's like the ESP status and all. So if I just close that, close all, kill all, I will just kill all, okay, all background threads are killed. So now that statistics will not send NXP status. So now if I use this date time sync, okay, so we got this gate time data, okay, and if I run that statistics send to command, okay, only one time, so it will send this data. So that Python server is actually looking for data. If the data is get time, it is actually sending command to NXP board so that it will correct its clock. And if in data there is a status, then it is the Python program which is running on port 5555. It will tell that Flask web app, and it will update the status here. Okay, so this is all happening. So you can control this littleOS, and at the end, actually the hardware through Wi-Fi from anywhere. You can run any number of threads, actually the 1,000 number of threads. Now actually I will be happy to actually explain all these codes, like how context is stored, how scheduling is happening. Okay, so all those things are very good, or I will say very interesting to play with. Okay, like just change the scheduling method. Okay, if we change the scheduling method to shed PRI, okay, priority scheduling, and if I run this print 100x and print 100o, okay, let's say print 100x, just let's run this print 100x. Okay, and if we say this statistics show, you will see the time is 5003 milliseconds. It is too much better when algorithm is priority scheduling. Okay, when algorithm was the RR. Okay, I will show that if shared RR, if algorithm is round robin, and then the print 100x will take around 6000 milliseconds. So why this very good turnaround time? Okay, so this is actually a good topic to discuss. Like you will say the print x took the 6000 milliseconds. So because of the round robin is made for a general purpose operating systems, not for a very response time hungry or operating systems or real time operating systems. So this is all thing actually. Uh, Actually, to the each file of the source, like multitasking or memory.c. Actually, memory.c there is nothing actually. But in IRQ, how we are handling IRQ, how NXP's IRQ handling works. Okay, all this will take some time, so I will discuss this in some future. If anyone actually needs, you can contact me anytime. So, or you can actually erase the, you can actually raise what it says issue on the GitHub. Okay, I will be happy to explain the code, what is happening, how I made this real-time operating system that is running on the ESP. Actually, you can use the exact code and change according to another board. Like you will only change the memory mapping, you will only change the how you will communicate with the LPUART or any peripherals. Okay, but the all logic for the uh, operating system will remain same. Okay, also we can think more about how scheduling should be happen, like what happen if in priority scheduling multiple threads got same priority, then what you will do. So these are very good topics to actually discuss and think about. So I did all this. Thank you.